Well, it's a pleasure to be here. I want to thank the organizers. And I've known Menachem my whole career. I learned all about large cardinals from his paper with Kanamori. It's been fantastic knowing him. Everyone said everything. So, and then James took my line that I could just confirm everything. So, what? Anyway. So I don't think I'm going to go the whole time, but we'll see what happens. And, I've always been in rooms without clocks, and I wonder why there are no clocks. I've never been in a room with a thermometer, though. So,
you know why you installed the temperature? There were a lot of complaints that either the overheated or it's too hot in the summer or too cold in the winter. So in order to the Department of Maintenance decided to install in every big lecture to store the temperature and say, if you complain about temperature, tell us, what? Sorry? So that was your decision as president?
no, it's fun to watch. Watch it as it goes up during the day. Okay, so I want to talk about how formulating the axiom V is ultimate L. And I want to use this. So just remember, you can formulate V equals L without defining L. There it is. You just say, for every sigma 2 sentence, if it's true in V, then you can reflect it into a minimal model. So there's no definition of L there, but that defines the axiom V is equal to L. So it's just test models. So you can do the same thing or try to do the same thing for an ultimate L, and that involves picking out the right test models. And we get those from determinacy. And so let me remind you the notion of universally bare. It's in a paper with Jifeng and Menachem. So it sets universally bare a set of reals if all of its continuous pre-images have the property of bare in any topological space. That's obviously not the right definition. That's just the easy definition. The usual definition is in terms of representations and the projections of trees that project the complements and forcing extensions. Okay, but the universally bare sets are a nice collection of sets. They couple into large sets because you really have to look at arbitrarily large in general spaces. If you have large cardinals, so a proper class of Woodin cardinals, then the universally bare sets have very nice closure properties. If A is universally bare, then every set that you can construct from A in the reals is universally bare. Now you need large cardinals for that. It's not too hard to show that if V is equal to L, then every set is the projection of a universally bare set. So the universally bare sets aren't even closed under continuous images if V is equal to L for the worst possible reason. Every set can be represented that way. The universally bare sets have all the usual regularity properties. They're Lebesgue measurable, they're Ramsey, they have the property of bare. So you can ask, now I'm going to go a little bit off topic because it is an interesting question, how much closure is provable from some large cardinal hypothesis? And this turns out to be related to whether there's an anti-intermodal theorem. So there's what's called the ceiling theorem. If delta is supercompact and you collapse 2 to the delta to omega, and then you take a forcing extension of that. Is there a laser pointer here? No. And then you take a forcing extension of that. So we're collapsing the 2 to the delta to omega, and then taking a generic extension of that. That's V of GH. We can form the universally bare sets in V of G, and we can form the universally bare sets in V of GH. Oh, okay, great, thanks. Okay, so that's what we're doing here. First, in each of these models, the universally bare sets are closed in the sense that if you construct from all of them, you don't get anything that's not universally bare. And then you can't change the theory in a very strong sense. There's a generic elementary embedding, in fact, a canonical one, that takes you from this model to this model. So let me remind you, there's an analogous theorem.
What do you exactly mean by the one constructing universal bare sets? You throw them in as...
Yeah, you throw them all in. You just throw them all in. So this is the smallest inner model which contains all the universally bare sets and the reals.
But you don't throw any evidence to the fact that
No, you're not throwing in any evidence. This is an L of P of R model, and it's a determinacy model. It's an 80-plus model. So you're just forming that model. And this is really an interesting, well, so you get this closure, and then much more than that, you get this invariance. So let me remind you of an old result that, and why this is an interesting question. And so the question is, could it be from some large cardinal hypothesis that you just get this outright? That if you construct from the universally bare sets and the reals, you don't get anything that's not universally bare, and you get the ceiling between V and any generic extension of V. Do you have to do this initial collapse if you chose a large cardinal hypothesis? So in the 80s, I showed that if you have a limit of strong cardinals and you collapse their sup to omega, you get full generic absoluteness for the projective sets. In fact, you get the projective sets are universally bare. Now, then you could ask, well, could you prove that theorem from a large cardinal hypothesis? Do you have to do the forcing? And the answer, of course, is, yeah, Woodin cardinals. Okay, so is this a precursor to that? Does this suggest that there's some large cardinal hypothesis that does the outright sealing? That would kind of complete that picture. So it's a little bit off topic. If there is a large cardinal hypothesis that does the outright sealing, that represents a failure, a place where inner model theory is going to have to fail. So the stakes are much higher. And I'll say just a little bit more about that later. But it's an interesting question. All right, back to these sets. So here we have A is universally bare. John already defined theta for me. Theta, in the sense of L of A and R, is the supremum of the ordinals onto which you can map the reals, of course, by a function in L of A and R. And if you have a proper class of Woodin cardinals, you don't need that much. If A is universally bare, then this ordinal, which measures as the size of the continuum here, is a Woodin cardinal in the Hod. And then that motivates formulation of the axiom V is ultimate L. The intuition is that, as in fact John talked about this, is that these should be L-like models. They in fact should be strategic extender models. So the universally bare sets are just handing us a wealth of naturally occurring strategic extender models. Well, if I was in my ultimate L or in my L, I just reflect into those. And so that's the formulation. Proper class of Woodins, just to make the universally bare sets nice, we just reflect sigma 2 sentences. So it's very much like that formulation of V is equal to L, except we're replacing or enlarging or changing our notion of test models. Pardon? Well, I'll say more about that in a moment, but if you're going to reflect sigma 2 sentences, it turns out it doesn't matter. It's the same. So, yes, okay. And that's, this issue is going to be very much at the core of what I'm doing. This is a weakening of the formulation of V is ultimate L that has been the official formulation. And the whole point of what I'm going to be saying today is why one's forced into this change.
Why one's forced
into this change? An intuition that at least some of us had, or maybe only I had, turned out to be completely wrong. It's not the last time that's going to happen. So, okay, John already defined the Solovay sequence. It's a series of approximations to theta. This is now in the context of AD. Theta 0 is the soup of the ordinals onto which you can map the reals by a function that's OD. And then you move from theta alpha to theta alpha plus 1. Instead of going from the reals, which is p omega, you go from the power set of theta alpha. Still requiring the function to be OD. You take soups at limit stages, and you stop when you reach theta. Okay. So these ordinals play an important role in the so-called Hod analysis. Now, if you assume AD plus, the Suslin cardinals are always closed in theta. A cardinal is a Suslin cardinal if there's a tree on kappa that represents a real. It's a set of reals that can't be written as a projection of the tree on any smaller cardinal. So omega is a Suslin cardinal, omega 1 is a Suslin cardinal. So they're always closed below theta. Theta alpha turns out to be a Suslin cardinal for every alpha less than omega. Omega was the index where you hit theta in the Solovay sequence. Theta alpha is a limit of Suslin cardinals if and only if alpha is bigger than 0 and alpha is a limit ordinal. So the successor theta alphas are always not a limit of Suslin cardinals. And the reason for bringing that up is we want to look at the large cardinal structure. So this is the Solovay sequence, and now let's fix some index and make alpha either 0 or not a limit ordinal. Then theta alpha is a Woodin cardinal in Hod. Let delta be the largest Suslin cardinal below theta alpha. That exists because theta alpha can't be a limit of Suslin cardinals. Then it's a strong cardinal in Hod cut to theta alpha. So the successor points of the Solovay sequence are Woodin and Hod. A Woodin cardinal always has a least thing strong to it, and that's the largest Suslin cardinal below. So there's a very kind of tight connection between some kind of large cardinal structure in Hod and the determinacy structure of the Suslin cardinals. So this is just part of a general connection. Okay, so the question is how much of this, well, here's a theorem. So there's no, it's just AD plus V is L of P of R. That whenever it's standard when you talk in the theory AD plus to assume V is L of P of R. And that's because we're interested in Hod. And if you don't assume V is L of P of R, you can code anything you want into Hod by stuff up above theta. So look at the Solovay sequence. Suppose you have an index, then the following are equivalent. Theta alpha is a Woodin cardinal in Hod, and alpha is 0 or a successor. So the only theta alphas that can be Woodin are the ones that were identified as Woodin. No other theta alpha can be Woodin. There's no assumption of a Hod analysis here. These are the kinds of things, the Hod analysis, which would be the analysis of Hod as a fine structure model, we would expect this to come out of that. But as is the case in the subject, sometimes AD plus just gives you enough information to prove these things outright. So here's the theta alpha conjecture. AD plus V is L of P of R. Suppose you have delta less than theta, and then the following should be equivalent. It's either a theta alpha for some limit alpha, that's 1, and 2, it's a limit of Woodin cardinals in Hod, and also such that for all kappa less than delta, kappa is not less than delta strong in Hod. So the limit theta alphas are conjectured to be the limits of Woodin cardinals which have no cardinal below that's strong up to that cardinal delta. All right, so now, so I'm going to be making lots of conjectures. Assume AD plus and V is L of P of R, then out of AD plus theory, the following are equivalent. ADR fails, and 2, there's a largest Suslin cardinal. So the models of AD plus not ADR, in which the largest Suslin cardinal is on the Solovay sequence, these are called the LSA models of AD plus, and they've been extensively studied by Grigor, who's done all kinds of stuff with them. So this is not really a special case of the theta alpha conjecture, but it's related. And it's an example where the AD plus theory just gives you enough of a handle so that you can prove something you would expect to be true. So AD plus V is L of P of R. We're now in the regime where ADR fails so that we have the largest Suslin cardinal. Then the following are equivalent. It's a limit of Woodin cardinals in Hod. And it's also on, that's 1, and 2, it's on the Solovay sequence. If it's on the Solovay sequence, it's a limit of Woodin cardinals, because every successor theta alpha is a Woodin cardinal. And so this is just saying the only way it can be a limit of Woodin cardinals is to be on the Solovay sequence. Okay, so it seems that if we want to look at the large cardinal structure of Hod, we'd like to restrict to models where there's a largest Suslin cardinal, because if there's a limit, if we're not in the ADR case, then theta can't be Woodin, and it just seems to have a more restricted structure. So let's just isolate that. Proper class of Woodins, gamma infinity will always denote all of the universally bare sets. We're going to look at proper initial segments of the universally bare sets. They're going to be closed in this sense, and will require that they're not a model of ADR. So these are 80 plus models of not ADR, so they have a largest Suslin cardinal. They could be of the form L of A and R, or gamma could be closed under sharps. Gamma could be very highly closed, but we're requiring that there be a largest Suslin cardinal. Okay, so the speculation was that if you take a gamma that's properly less than gamma infinity in this sense, then if you look at these models, these can provide a better approximation to V in the context of V as ultimate L. The idea being here is, well, wait a minute. I mean, theta is a Woodin cardinal here. So we're cutting Hod at a Woodin cardinal. We have all kinds of stuff below. So it seems reasonable. You've got strong cardinals in this model and so forth. It seems reasonable that, well, maybe if you just make gamma more and more closed, you can reflect more and more sentences into these models. We don't want to look at ADR models because by the theta alpha conjecture, there can't be any strong cardinals in M. So since we're trying to mirror V in V as ultimate L, we don't want to look at the ADR models, which is the point of this definition. Okay. All right, so I want to just state a lemma that's quite useful. I have to set up some notation. I'm always going to be looking at point classes within the universally bare sets that satisfy the properties that I stated. Delta gamma will be the largest Suslin cardinal of L of gamma R. Theta gamma will be the theta. And let me just draw a picture, because the picture makes it clear. This is L of gamma of R, and this is the theta. Here's the largest Suslin cardinal, delta gamma. This is theta gamma. Now we're taking a point class smaller than gamma, so maybe it looks like this, but its theta goes past this largest Suslin cardinal. So this is L of sigma r. This is the theta sigma. And what this theorem is saying, or what the conclusion is it follows fairly easily that delta sigma has to be delta gamma. That's just by the coding lemma. So if this theta lands between here and here, this has to be the largest Suslin cardinal here. What the theorem is saying is that the Hod here, up to here, the Hod here computed in this model is a rank initial segment of the Hod here. Okay, so that's not at all obvious. It's saying the Hod of the smaller one cut at its theta is a rank initial segment of the Hod of the larger model. Okay, so if you want to think of this as an ascendance, as you ascend through point classes, freezing the largest Suslin cardinal, Hod can never generate new bounded sets. Okay, so that's what the theorem is. Hod alignments. It's saying that the Hods cut at the thetas line up by rank. Okay, so this has a corollary, and this answers that sigma 2 question. Suppose you have a proper class of Woodin cardinals and the following are equivalent. For every sigma 2 sentence, you can reflect it into the Hod of L of A and R for some universally bare set. And the second statement is for every sigma 2 sentence, if it holds in V, you can reflect it into the Hod cut at theta of some L gamma and R. Okay, well, that's just immediate from this. If you can reflect into here, well, we can choose an A, take sigma now as an A whose theta lands above the witness for that sigma 2 sentence. So this witness of the sigma 2 sentence is here, but this is a rank initial segment of this, so the sigma 2 sentence, the witness, it's still a witness. So we're just using the fact this is a rank initial segment of this, and these ranks can come all the way up to this. So if a sigma 2 sentence holds here, it holds here for a large enough sigma, and large enough sigma of the form given by a single set A. Okay, so if we want to reflect sigma 2 sentences from V, we might as well reflect into L of A and R, and that's immediate by Hod alignments. Okay, so now let's assume that these Hods cut at theta, the L gamma of ours, can provide better approximation. Let's do two possible variations of V as ultimate L. Axiom 1 would be a proper class of Woodin cardinals, proper class of strong cardinals, and now let's reflect sigma 4 sentences, but not into the Hod of L of gamma R, the Hod of L of gamma R cut to the theta of L of gamma R. So we're assuming that these models can resemble V more closely. And then axiom 2 is exactly the same, except we restrict to sigma 3 sentences, but we simplify the model by simplifying gamma to the form of L of A and R. All right, now this Hod alignment business tells you that axiom 1 implies axiom 2. Because if you can, and the whole point is if you've got a sigma 3 sentence true here, and gamma is, well, if gamma is of the form L of A and R, I don't have to do anything. If it's not, gamma's closed under sharps for reals, that's kind of irrelevant. If I have a sigma 3 sentence here, I can pick all the witnesses up by some stage, choose sigma from A that's above that stage, and now by Hod alignment, the sigma 3 sentence is true here. I have all the witnesses, and I'm a rank initial segment. So any sigma 3 sentence that can hold in an L gamma of R can hold in an L of A and R, and the Hod of an L of A and R cut at theta.
Did you have A also in axiom 1, or did you have to?
In axiom 1, it was only A's. Axiom 1 was not just A, it was a gamma. Yeah. So the idea is the situation here is we're trying to reflect more sentences. And that suggests we may have to make gamma richer. Then if the gamma given by a single A is very simple. But maybe we need gamma closed under sharps or daggers or much, much more if we are interested in more complicated sentences. So this says there should be some closure that enables you to reflect sigma 4 sentences. Okay, say. But if you can do that, then you can reflect sigma 3 sentences into the HODs of the L of A and R's cut at their thetas. That's axiom 2. We can't reflect sigma 4, at least I don't know that. But if you can reflect sigma 4 into any HOD cut at theta, then you can always reflect sigma 3 into the simpler HODs of the L of A and R's cut at theta. The point is that the L of A and R is easier to write down. Oops, sorry. So axiom 1 is there are two parameters in these axioms. How rich is the determinacy model you're trying to reflect into the HOD of? And you're always trying to reflect into the HOD cut at theta. So how rich is that gamma? Is it just given by a single set, like L of A and R? And the second parameter is how complicated a sentence? Okay, so if I were thinking about L as reflecting into the test models, if V is equal to L, you can reflect any sentence in, right? By condensation. If these HOD models are the true good test models and V is ultimate L, I would expect, by analogy, to reflect any sentence in. It's just I don't know what the gamma is. So that's the space we're exploring here. Okay? And then what it's saying is if that picture is right, then you can reflect sigma 3 sentences into the simpler HODs given by a single set. All right, so why do this? Well, so the theorem is axiom 1 implies axiom 2. That suggests using axiom 2 for the formulation of V is ultimate L, and that's what I've been using. Now, why care? When you formulate the axiom, you want to see what you can prove from it. The more large cardinals you can have present in the axiom and the more reflection you can allow, it's easier to use the 80+ machinery to get consequences. That's the only reason. So what are some consequences out of V is ultimate L from now this is just using 80+. Well, you have CH. This ties into what Ralph was talking about and connects with what he was doing, actually. If V is ultimate L, you can prove V is not a generic extension. It's its own mantle. Okay? You can also prove V is equal to HOD from V is ultimate L. Now, these are all much easier to prove from axiom 2 than from V is ultimate L. And that was the point of using the formulations like axiom 2 for ultimate L. It was just easier to get these consequences. Okay, I will confess I am not going to finish early. Axiom 2 implies the omega conjecture. That was another reason for axiom 2. But I don't know that from the formulation of V is ultimate L. I need the theta alpha conjecture. So that's a case where the weaker form of just reflecting sigma 2 sentences, even with the 80+ machinery we have, is now deficient, can't quite get consequences that we would like the HOD conjecture. Now, one only needs a weak version of the HOD conjecture, and that's the conjecture that if you have 80+ plus V is L of P of R, then there are at most finitely many Woodin cardinals in HOD below theta. Right? Because if there were omega many Woodin cardinals below theta, the soup of the first omega Woodin cardinals has to be theta omega by the theta alpha conjecture. So there can't be infinitely many Woodin cardinals below theta 0 if the theta alpha conjecture is true. In fact, it should be the case that theta 0 is the least Woodin cardinal in Hod, and 80 plus almost does that for us. If you assume 80 plus v is L of p of r, then for a cone of x, theta 0 is the least Woodin cardinal in Hod sub x. And it's thought if you can prove something on a cone, it's got to be true light phase, but sometimes the light phase, many times, the light phase proof is much, much harder. All right, but, well, still, why not use axiom 2? All right, so I'm going to go much faster now. This is the notion of a weak extender model for supercompact. You've probably all heard me make this definition many times. N is an inner model of ZFC containing the ordinals. N is a weak extender model for delta supercompact. If for all lambda bigger than delta, there's a normal delta complete fine ultrafilter on p delta lambda such that n intersect p delta lambda is in U and U intersect n is in n. So the idea is if you're going to build an extender model for supercompact, you would and you're backgrounding it, you would expect to produce a weak extender model for supercompact. And then you can analyze these models and get lots of interesting properties. And I'll state one. So again, this has already been defined for us. But let me just remind you, if n is an inner model of ZFC containing the ordinals, E is an n extender of length eta if there's an elementary embedding from n into a transitive class. Critical point of J is less than eta. And E is just a set of pairs A, J of A intersect eta, where A is a subset of eta in M. Okay? Extenders are usually presented as systems of ultrafilters, but this is fine for our purposes. If E is an extender of length eta, then one can define the ultra power as an n extender of length eta. Then you can define the ultra power of n by E, and that recovers E. Okay, so there's no loss of information. There's no strength assumption here at all. There's no strength. So kappa E is the critical point of E, and that's the notation. So here's the universality theorem, which shows why weak extender models are interesting. This is the sharpest possible version. So sharper than the versions I've previously stated. If n is a weak extender model for delta supercompact, E is an end extender of length eta with critical point greater than or equal to delta, and we have the corresponding embedding, then the following are equivalent. The extender is in the model, and for every, that's 1, and 2, every subset of eta that's in the model, E of A intersect eta is in N. This has to be true if the extender's in the model, trivially, and that's equivalent to the extender being in the model. There's no assumption on strength here. It's any embedding whatsoever. So weak extender models have a remarkable universality property. This basically says all large cardinals go down. Here's some corollaries. There's no non-trivial elementary embedding J from n to n whose critical point is greater than or equal to delta. That gives you an n extender that has to be an n and violates Kunin. Curiously, you can have J from n to n with critical point less than delta. So in the universality theorem, the constraint that the critical point of the extender be greater than or equal to delta is necessary. What about downward closure? Here's a typical transference that you get. If kappa bigger than delta is a Woodin cardinal in V, then kappa is a Woodin cardinal in N. And the point is that you can witness Woodinness in V by extenders that are cohering N, and those extenders are in N. And this works for everything. You just take any large cardinal hypothesis, you can kind of do a coherent form of it, and they all go down. Okay, so why not use axiom 2 for V as ultimate L? Well, however one's going to formulate V as ultimate L, one's only interested in the axiom if you can prove this conjecture. Suppose delta is extendable. There's a weak, the conjecture is that there's a weak extender model n for the supercompactness of delta. N is included in HOD, and n satisfies V as ultimate L. If one can prove this conjecture, then there's no Scott's theorem for ultimate L. Ultimate L is consistent with all large cardinals by the universality theorem. Okay, so that's the point. So now we have to be careful how we formulate V as ultimate L. So one last conjecture, call it the HOD ultrafilter conjecture.
What's wrong with axiom 2?
Well, I'm getting to that. Patience, patience. I'm keeping you in suspense. I didn't want to give a 2-minute talk. Suppose L of A and R, so here's the HOD ultrafilter conjecture. And now I'm just going to localize to 80 plus models of the form L of A and R, because that's all you have to. Suppose you have an ultrafilter in the HOD of L of A and R, and the HOD of L of A and R thinks U is a countably complete filter. Ultrafilter, sorry. So you just have a countably complete ultrafilter in HOD. The conjecture is that U generates a countably complete filter. What I mean by that is take any countable number of sets in U, but intersect them in V. The intersection is non-empty. Now the HOD ultrafilter conjecture implies that omega 1 is the, what? No, it's non-empty. Yeah, so I'm abusing notation. When I say generates, I mean close under countable intersections. Okay? Okay, look, the HOD ultrafilter conjecture implies that omega 1 has to be the least measurable cardinal in HOD, clearly. But that was already known from 80 plus. Omega 1 is the least measurable cardinal of HOD. That's an 80 plus theorem. It doesn't need the HOD analysis. And you can actually prove that the HOD ultrafilter conjecture holds if you restrict to ultrafilters on omega 1. HOD looks like L mu at omega 1. And that was known before for a long time. And there's a little bit more evidence. It's misleading, but it just shows you that you can get non-trivial instances. Again, it's exploiting 80 plus machinery. If you have in an 80 plus model, if you enlarge HOD by going to HOD sub B for some B in L of A and R, then you get the HOD ultrafilter conjecture relative to the larger B. So you can always enlarge HOD so that every countably complete ultrafilter is countably complete. This is not real evidence, though. Let me be truthful. In this enlargement, we've made HOD small. There's only one Woodin cardinal. So what's going on here is there's something called a hybrid analysis, and there is a HOD-like analysis for this model. This is a fine structure model, turns out. All right. Whoops. Technical theorem, I'm almost done. This is another, it uses that same machinery. Suppose you have an L of A and R model of 80 plus. You have an L of R cardinal. You have a cardinal of HOD below theta. And you look at the cardinal successor in L of R. Kappa may not be a cardinal in L of R, but go to the first cardinal above. Then there's a countable subset of lambda in L of A and R that can, or in V, it doesn't matter, which cannot be covered by any set in HOD of order type less than kappa. That's what we want. What's the proof really showing? If you take any inner model of L of A and R that's a model of ZFC, if lambda is an uncountable cardinal in L of A and R, and lambda is less than theta, less than or equal, then lambda is a limit of strongly inaccessible cardinals of n, which have countable cofinality.
Who is kappa in the theorem?
What?
Yeah. Or is that
That's given.
Oh, okay. Yeah.
So you're in an 80 plus model. Take any uncountable cardinal of the model below theta. Take any inner model of ZFC. then that cardinal is a limit of strong inaccessibles of the inner model of ZFC, which have true cofinality omega. Okay, well, if you have that, you get this trivially. Sigma is just a cofinal set in a strongly inaccessible of HOD is certainly a model of ZFC, and you just choose that strong inaccessible of countable cofinality. So this uses that machinery, the hybrid analysis, and now we get a theorem. Suppose we have L of A and R as a model of AD plus, and that the HOD ultrafilter conjecture holds for L of A and R. Take any cardinal of HOD cut at theta, then in HOD cut at theta, kappa cannot be lambda strongly compact, where lambda is the first L of R cardinal above kappa. You have a failure of strong compactness. And the proof's immediate. Assume not. Well, let's let U be the ultrafilter that witnesses that HOD thinks is a kappa complete fine ultrafilter on P kappa lambda. So remember, lambda is an L of R cardinal. Since the HOD ultrafilter conjecture holds, U has to generate a countably complete filter. Well, we have a countable subset of lambda that can't be covered by a set in HOD of size less than kappa. That's a contradiction. Symbol V past the level of sigma 2 sentences, they can't have supercompact cardinals in them. So the HOD of an AD plus model cut at theta can have a strong cardinal, because theta can be Woodin. It cannot have a supercompact cardinal. In fact, the supercompact cardinals have to exist in very narrow ranges from the point of view of the L of A model, the apparent AD model, because supercompactness can't even reach an L of R cardinal. So that means that when you formulate V is ultimate L, you can't use sigma 3 sentences because clearly V has a supercompact and you can't reflect supercompact into these test models. So you better stick with sigma 2. That's it.
Any question for you?
So they can't reach, the strong compactness can't reach the next L of R cardinal,
Right.
but it can reach lots of HOD.
Oh, yeah, yeah. You can have rank, if the ultimate L conjecture is true, the rank initial segments of HOD which have any sigma 2 sentence true, that's true. You know, you have huge cardinals, rank into ranks, and so forth. But if you try to, but everything's in very tight ranges. So what it's saying is, by looking at, so this is a kind of more of a philosophical,
Basically, can't reach the next cardinal.
they can't even reach the next L of R cardinal. So they exist. I mean, this has some consequences for the HOD analysis. It shows that, so this will make sense for those of you. It does show that if you can have supercompacts in HOD, local supercompacts, then you can have Woodin cardinal cut points of HOD, which are not only on the theta alpha sequence, they're not even L of R cardinals. So the idea that you characterize the successor theta alphas as the Woodin cardinal cut points of HOD can't be true. So that says something about the HOD analysis. It's saying that, because one would have expected that the Woodin cardinal cut points have to be on the Solovay sequence. And this is saying no. Not only are they not on the... Well, because suppose you had a supercompact past a Woodin and HOD, right? We'll take the least occurrence of that. That's going to give you a Woodin cardinal cut point of HOD with something below it that's supercompact up to it, right? Just eliminating the first overlapping extender. So we have a Woodin cardinal cut point of HOD such that there's a supercompact in that initial segment of HOD. But that can't be an L of R cardinal. So it certainly can't be on the Solovay sequence. It's in fact can't, you know, so that intuition was wrong. Oh. I guess the duty